Every person over 50 knows this. The weather changes, and your knees know before the forecast does. Your joints ache before the rain arrives. Your back stiffens when the pressure drops. Your headache starts hours before the storm. And for decades, maybe your whole adult life, you have been told this is in your head, that the science is inconclusive, that correlation is not causation, that it is just a feeling. Well, it is not a feeling, it is physics. And the physics is the same physics that governs deep-sea divers, carbonated beverages, and the decompression sickness that kills people who surface too fast. Let me show you what is actually happening inside your body when the weather changes. Right now, as you listen to this, the atmosphere is pressing down on every square centimeter of your body. At sea level, that pressure is 101,325 pascals, approximately 14.7 pounds per square inch. That is the weight of a column of air extending from your skin to the edge of space, roughly 100 kilometers straight up, pressing on you from every direction. Top of your shoulders, sides of your rib cage, surface of your eyes, every exposed inch. You do not feel it. You do not feel it because the pressure inside your body matches the pressure outside. Your tissues are pressurized. Your blood is pressurized. The fluid inside your joints, the air inside your lungs, the gas dissolved in your blood, all of it has equilibrated to atmospheric pressure over the course of your entire life. The push from outside and the push from inside are equal. They cancel. You walk around in a state of perfect pressure equilibrium without ever thinking about it, in the same way a fish does not think about the water pressing on its body from every side. But equilibrium is fragile. It depends on the outside pressure staying constant. And it does not stay constant. The atmosphere is not a static system. It is a fluid. A massive, turbulent ocean of gas driven by solar heating, planetary rotation, and temperature differentials between the equator and the poles. Weather systems move through it continuously. High-pressure systems bring clear skies and stable conditions. Low-pressure systems bring clouds, moisture, and falling barometric pressure. These shifts can happen over hours. A weather front passing through a region can drop the local barometric pressure by 10 to 20 millibars in the span of an afternoon. That does not sound like much. 20 millibars is roughly 2% of total atmospheric pressure. But your body is not a rigid container. It is a collection of soft tissues, fluid-filled cavities, dissolved gases, and flexible membranes, all of which were calibrated to a pressure that just changed. And the recalibration is not instant. It takes time. Different amounts of time for different systems. Your lungs equalize quickly. Your blood pressure adjusts within minutes. But the gas pockets in your joints, the dissolved gases in your synovial fluid, the air trapped in your sinuses, these equalize slowly through narrow channels and across semi-permeable membranes. During that window, while the outside pressure has dropped, but the inside has not yet caught up, physics happens. Specific, measurable, equation, governed physics. And you feel it. Here is the first equation. In 1662, an Irish natural philosopher named Robert Boyle published a discovery that became one of the foundational laws of gas physics. Boyle was working with a J-shaped glass tube, sealed at one end, trapping a column of air and measuring what happened when he added mercury to the open end, increasing the pressure on the trapped gas. He found a precise, repeatable relationship. When he doubled the pressure, the volume of the trapped air halved. When he tripled the pressure, the volume fell to a third. The relationship was exact. Pressure times volume equals a constant at constant temperature. PV equals a constant. Boyle published this in a book called New Experiments, Physico-Mechanical, and the result has been verified millions of times since then in contexts from weather balloons to diving equipment to the behavior of gas bubbles in industrial piping. It is not controversial. It is not debated. It is one of the most replicated results in the history of experimental science. And it applies to every pocket of gas on Earth, including the ones inside your body. Your joints contain gas, not large visible bubbles, but small pockets of dissolved nitrogen and carbon dioxide in the synovial fluid, and sometimes tiny gas accumulations trapped within the joint capsule itself. These are normal. Everyone has them. You can sometimes hear them. That cracking sound when you flex your knuckles is, in many cases, a gas bubble rapidly forming or collapsing in the synovial fluid under changing pressure. When atmospheric pressure drops before a storm, Boyle's law applies to every one of those gas pockets. The external pressure has decreased. The gas, at constant temperature, must increase in volume. Not by much, we are talking about fractions of a milliliter. But the joint capsule is a confined space. It has walls, it is not infinitely expandable, and those walls are lined with nerve endings, mechanoreceptors that detect stretch, pressure changes, and deformation with remarkable sensitivity. A volume change of even a tiny fraction of a milliliter is enough to increase the mechanical load on those nerve endings. They fire. They send a signal along the nerve fibers to your spinal cord and brain, and you register it as an ache, as stiffness, as the nagging, persistent sense that something is wrong in a joint that was perfectly fine yesterday afternoon. That dull ache you felt last Tuesday morning before you checked your phone and saw the rain icon on the weather app. This is what was happening inside your knee. Gas expanding in a confined space, pressing on nerve endings, following an equation published over 360 years ago. Your joint was obeying Boyle's law. It had no choice. No gas pocket anywhere in the universe has a choice. Pressure drops, volume rises. That is the law. But Boyle's law is only the first layer. There is a second equation operating at the same time, and to understand it, you do not need a physics textbook. You need a bottle of sparkling water. Open the cap. Listen to the hiss. Watch the bubbles appear. Dozens of them rising from nowhere, forming on the inside of the glass where a moment ago the water was perfectly still and clear. Those bubbles were not hiding. The carbon dioxide was dissolved in the liquid, held in solution by the elevated pressure inside the sealed bottle. The moment you cracked the cap, the pressure above the liquid dropped, and the gas that was dissolved at the higher pressure could no longer stay dissolved at the lower pressure. It came out. It formed bubbles. That is all fizzing is. Dissolved gas leaving solution because the pressure changed. In 1803, an English chemist named William Henry, working in Manchester, proved that this relationship is precise and proportional. The amount of gas that dissolves in a liquid is directly proportional to the pressure of that gas above the liquid. More pressure, more gas dissolves. Less pressure, less gas stays in solution. This is Henry's law. And you have watched it operate every time you opened a can of soda. Now here is where it matters. Your synovial fluid, the clear, viscous liquid that lubricates your knees, hips, shoulders, and every other synovial joint, contains dissolved gases. Nitrogen, oxygen, carbon dioxide, all dissolved at concentrations set by the atmospheric pressure your body has been equilibrated to. Under stable pressure, those gases stay quietly in solution. You never know they are there. When barometric pressure drops before a storm, Henry's law applies to your joints the same way it applied to the sparkling water. Some of those dissolved gases can no longer remain in solution at the new, lower pressure. They come out. They form microbubbles. Tiny gas pockets inside the joint space that were not there an hour ago. These microbubbles take up physical space in a confined cavity, adding to the volume expansion that Boyle's law is already causing. And they interact with the synovial membrane and cartilage surfaces in ways that trigger low-grade inflammatory signaling. Your joint is now experiencing both mechanical stretch from the expanding gas and chemical irritation from the newly formed bubbles, simultaneously from the same cause. A drop in atmospheric pressure. So that is two equations operating at the same time inside the same joint. Gas pockets expanding. Dissolved gas coming out of solution. Both governed by laws published centuries ago, both acting on the nerve endings in your joint capsule. And here's the connection that changes how you think about this entirely. You may have heard of decompression sickness, the bends. It is one of the most feared hazards in diving. A scuba diver descends to 30 meters. At that depth, the water pressure is 4 times atmospheric. Henry's law forces large amounts of nitrogen from the air. The diver breathes into solution in the diver's blood, joint fluid, and tissues. The nitrogen dissolves invisibly. The diver feels nothing unusual. The gas is harmless as long as the pressure stays elevated. Then the diver surfaces too fast. The pressure drops from 4 atmospheres to 1 in minutes. Henry's law reverses. The dissolved nitrogen can no longer stay in solution. It comes out not as microbubbles, but as substantial gas pockets that form in the bloodstream, in the joint spaces, in the tissues surrounding the spinal cord. The diver feels sudden, severe joint pain. In extreme cases, the bubbles block blood flow to the brain or spinal cord, causing paralysis or death. Your arthritic knee before a rainstorm is the same equation, the same mechanism, dissolved gas coming out of solution because the pressure dropped. The difference is scale, not kind. A diver experiences a pressure change of 3 full atmospheres in minutes. You experience a change of 20 millibars, about 2%, over hours. Henry's law does not care whether the change is large or small, fast or slow. It operates the same way at every scale. The next time your knee aches before the rain, your body is experiencing a miniature, slow-motion version of the bends. That is not a metaphor. That is a description of the physics. The same dissolved gas, the same equation, the same mechanism that sends divers to hyperbaric chambers, playing out gently, slowly, inside the joint you are rubbing right now. But pressure is not the only thing that changes before a storm. Temperature drops too. And temperature has its own separate physics operating on the same joints at the same time. Synovial fluid is not water. It is a non-Newtonian fluid, a complex biological mixture of hyaluronic acid, lubricin, phospholipids, and various proteins suspended in a plasma filtrate. Its viscosity, its thickness, its resistance to flow depends on temperature. And the relationship is not gentle or linear. It follows the Arrhenius equation, named for Svante Arrhenius, the Swedish chemist who described how reaction rates and fluid properties change with temperature. Viscosity increases exponentially as temperature decreases. Not proportionally, exponentially. A 5-degree drop in temperature does not make the fluid 5% thicker. It can make it substantially thicker, enough to measurably change how the joint performs. What this means inside your knee is straightforward. When the temperature drops 5 or 6 degrees before a storm front, the synovial fluid in your joints gets thicker. It flows less readily into the contact zones between the cartilage surfaces. It lubricates less effectively. The cartilage surfaces that glide past each other with almost no friction at 37 degrees Celsius. Normal core body temperature generate noticeably more resistance at 33 or 34 degrees. And the peripheral joints are the ones that cool fastest. Your knees, your fingers, your ankles and toes. The joints farthest from your body's core with the least blood flow to maintain temperature, the most exposed to ambient cooling. Their synovial fluid thickens first. You feel this as stiffness, as the sense that your joints need to warm up before they work properly. You might pace around the kitchen for 10 minutes before your knees feel normal. You might run your hands under warm water before your fingers stop feeling wooden. That is not a figure of speech. That is not your imagination. Your joints literally need to warm up. The viscosity of the fluid inside them must decrease before the joint can move freely. That morning stiffness on cold, damp days, the 15 or 20 minutes of cautious movement before everything loosens, is the Arrhenius equation resolving itself in real time inside your body. The fluid is thinning as your joint warms from movement and blood flow. The physics is playing out. You can feel the exact moment it finishes. So now you have 3 mechanisms operating simultaneously before a storm. Gas expansion from Boyle's law, microbubble formation from Henry's law, increased viscosity from the Arrhenius equation, pressure dropping and temperature dropping at the same time, each activating a different physical mechanism, all converging on the same joints at the same moment in the same body. Put your hand on your knee right now. That joint, that specific joint, the one under your palm, contains gas pockets, dissolved gases, and a viscous lubricating fluid, all governed by equations that are centuries old. On a stable, high-pressure day, all 3 systems are in equilibrium and you feel nothing. When a front moves in and the barometer drops, all 3 shift at once. The gas expands, the bubbles form, and the fluid thickens. 3 equations, 1 joint, 1 ache, and you have been told It is in your head. 3 centuries of physics says otherwise. But here is what I want you to understand next, because this is the part that explains why it gets worse as you get older, and it has nothing to do with imagination. Healthy cartilage is extraordinary material, 2 to 4 millimeters thick in a knee joint. A vascular, no blood vessels. A neural, no nerve endings. It is a biological shock absorber designed to do one thing: absorb mechanical stress so that the structures beneath it never feel it. Pressure fluctuations in the joint capsule, the kind caused by weather changes, are absorbed by healthy cartilage and dissipated before they ever reach anything that can feel pain. The gas still expands, the microbubbles still form, the fluid still thickens. All of the physics still happens. But healthy cartilage acts as insulation between the physics and the pain receptors. When you are 25, your cartilage is thick and intact. A 20 millibar pressure drop produces all 3 effects inside your knee: gas expansion, microbubble formation, viscosity increase, and you feel nothing. 0. The insulation absorbs every bit of it. When you are 40, the cartilage has started to thin, particularly in load-bearing areas: the medial compartment of the knee, the hip socket, the joints of the lower spine. You might notice a faint stiffness on cold mornings that was not there a decade ago. The insulation is still present, but it is wearing. When you are 55 or 60, that cartilage has been compressed and released roughly 200 million times. 200 million cycles of load-bearing, shock absorption, and elastic recovery. In some areas, it is thinned to less than a millimeter. In others, the spots that bore the most weight, absorbed the most impact, endured the most repetitive stress over decades. It is worn through entirely, exposing the subchondral bone beneath. And subchondral bone is innervated. It has nerve endings. Nociceptors. Pain receptors specifically tuned to detect mechanical pressure, chemical irritation, and the kind of microenvironmental changes that weather-driven gas expansion produces. Without the cartilage buffer, the physics reaches the nerve endings directly. The same Boyle's law expansion, the same Henry's law microbubbles, the same Arrhenius viscosity increase, all of it now landing on exposed, sensitive bone that was never supposed to feel any of it. This is why your grandmother was right and your doctor was evasive. The physics does not change with age. The insulation does. A 20-year-old and a 60-year-old experience exactly the same gas expansion in their knee joints during a pressure drop. The 20-year-old feels nothing. The 60-year-old feels everything. Not because the 60-year-old is imagining it, because their cartilage is thinner. The signal that was always there is finally getting through. And I find that remarkable. Not because the physics is complicated, but because it means your grandmother was right and your doctor was evasive. The mechanism was there the whole time. The insulation just wore down. Because your joints are not the only pressure-sensitive system in your body, not even close. In your carotid arteries, the major blood vessels on either side of your neck, and in your aortic arch, there are specialized mechanoreceptors called baroreceptors. These are stretch-sensitive nerve endings embedded in the vessel walls. Their job is to detect changes in blood pressure. When the arterial wall stretches more than usual, indicating higher blood pressure, they fire rapidly. When it stretches less, lower pressure, they fire slowly. Your brain uses this signal to regulate your cardiovascular system in real time. Heart rate, vascular resistance, fluid distribution, all continuously adjusted based on baroreceptor input. These sensors are remarkably sensitive. They can detect pressure changes of less than 1%. They evolved to do a specific job. Detect when you stand up, when you lie down, when you change altitude, when you exert yourself, any situation where blood pressure shifts and the brain needs to compensate to keep blood flowing to your organs, especially your brain. Baroreceptors do not distinguish between internal pressure changes and external ones. A drop in atmospheric pressure changes the transmural pressure across your arterial walls, the difference between the pressure inside the vessel and the pressure outside. The baroreceptors detect it. They cannot tell whether you stood up too fast or a low-pressure system moved in from the Atlantic. The signal is the same. Your autonomic nervous system responds, adjusting heart rate, redistributing blood flow, altering vascular tone throughout your body. You may feel lightheaded, fatigued, vaguely uneasy in a way you cannot name and cannot trace to any specific cause. You might wake up on a gray morning feeling inexplicably heavy, as if your body wants to stay in bed for reasons your conscious mind cannot identify. The pressure dropped overnight. Your baroreceptors detected it while you were sleeping. Your autonomic nervous system has been adjusting all night. You wake up in a body that has already responded to a weather change you have not yet observed. This is not anxiety. It is not a bad night's sleep. It is not psychosomatic. It is your cardiovascular system detecting a real, physical change in atmospheric pressure and adjusting your physiology in response. Your body registered the approaching storm before the clouds were visible. The baroreceptors did what they were built to do. The fact that they were built for altitude regulation and not weather prediction does not matter. Physics does not care about intended function. There is one more system, and it explains the symptom that arrives earliest and bothers people most. Your skull contains air-filled cavities called sinuses. The frontal sinuses above your eyebrows, the maxillary sinuses in your cheekbones, the ethmoid sinuses between your eyes, and the sphenoid sinuses deeper inside, behind the nasal cavity. Together, they form a network of sealed chambers inside your skull, all connected to the outside atmosphere through narrow drainage channels called ostia, passages only a few millimeters in diameter. Under normal conditions, pressure equalizes easily. Air flows through the ostia in both directions. Inside matches outside. You never think about it. The ostia are narrow, though, and they are lined with mucous membrane, the same type of tissue that lines your nasal passages, that swells in response to cold air, allergens, dust, infection, or the low-grade chronic inflammation that many people develop with age. When the membrane swells, the ostia partially close. The drainage channel narrows to a slit, and when atmospheric pressure drops rapidly, as it does before a storm, the air trapped inside the sinus is momentarily at higher pressure than the atmosphere outside the skull. Boyle's law again. The same equation. But now the confined gas cavity is not your knee joint. It is inside your skull. The higher pressure air inside the sinus pushes outward against the sinus walls. If the ostia were fully open, the pressure would equalize in seconds. Air would simply flow out through the drainage channel until inside and outside matched. But the ostia are partially blocked. The equalization is slow or stalled. The sinus wall, which is lined with pain-sensitive nerve endings, registers the pressure differential. The result is a headache. A specific kind of headache, pressure behind the eyes, across the forehead, deep in the cheekbones, that arise before the rain starts. Research has confirmed this. A 2015 study published in the journal Internal Medicine followed migraine patients and tracked barometric pressure simultaneously. They found that pressure decreases of 6 to 10 hectopascals were significantly associated with migraine onset. The patients were not imagining the connection. The atmospheric pressure data matched their symptom diaries. The physics predicted the pain, and the clinical data confirmed it. Enclosed gas cavity, pressure differential, blocked equalization channel, pain. The mechanism is simple enough to fit on an index card. So here is where we are now. Here is what is actually happening inside your body when the weather changes. Your joints contain gas pockets governed by Boyle's law. Pressure drops, volume expands, nerve endings detect the stretch. Your synovial fluid contains dissolved gases governed by Henry's law. Pressure drops, microbubbles form, adding volume and triggering irritation. Your synovial fluid follows the Arrhenius equation. Temperature drops, viscosity increases exponentially, lubrication fails, friction rises. Your cartilage, the insulation that shielded your nerve endings from all of this for decades, has thinned with age, with use, with the simple accumulation of 200 million compression cycles, and now the signal that was always there gets through. Your baroreceptors, the pressure sensors in your major arteries, detect atmospheric changes of less than 1%, and trigger autonomic adjustments you experience as fatigue, unease, and lightheadedness. Your sinuses, sealed cavities inside your skull, resist pressure equalization when their drainage channels narrow, producing headaches that precede the storm by hours. Every one of these is physics, measurable, calculable, governed by equations written in the 17th, 18th, and 19th centuries by Boyle, Henry, Arrhenius, and the physiologists who mapped the baroreceptor reflex. There is nothing mysterious about any of it. There is nothing subjective, nothing psychosomatic, nothing that requires belief or anecdote or hand, waving to justify. The equations are old, the mechanisms are well understood. The only thing that was missing was someone connecting the physics you learn in a classroom to the pain you feel in your body. You were never imagining it, not once. Your body was doing exactly what the physics predicted it would do. The gas expanded because the pressure dropped. Boyle's law, 1662. The bubbles formed because dissolved gas came out of solution. Henry's law, 1803. The fluid thickened because the temperature fell. Arrhenius, 1889. The cartilage that once absorbed all of this wore thin over decades and millions of compression cycles, and the nerve endings underneath started receiving a signal they were never meant to feel. Your cardiovascular system detected the pressure change through baroreceptors that evolution built for a different purpose. Your sinuses registered the imbalance and produced pain because their equalization channels were too narrow to compensate in time. It was always real, every single time. Every aching morning, every stiff afternoon, every headache that arrived before the clouds did, real. Governed by physics, governed by equations, governed by the same laws that govern diving bells and carbonated water and weather balloons. And the next time your knees ache before the rain, before the clouds have formed, before the forecast has updated, before anyone around you has noticed the sky changing, you are not guessing about the weather. You are not relying on folklore or superstition or the memory of your grandmother's complaints. You are detecting a real change in atmospheric pressure through at least 4 independent physical mechanisms operating simultaneously inside your body, in your joints, in your blood vessels, in your skull. Your body is a barometer. It always has been. The physics was never in your head. It was in your joints.